Good afternoon, everyone, and welcome to our TACO Tuesday webinar series. Today's discussion is going to be LoadMatch and LoFlo single piping systems. My name is Rich Medairos. I'm one of the senior systems engineers here at TACO. Today's presentation will be by Brett Zerba. Brett will get on in a moment, introduce himself. I will be the moderator, so I will watch for questions from the audience. And what we'd like you to do is to initially, if you could, there is a hand wave thing. If you could click on that, that way we know that we're broadcasting and that you can see our introductory screen. The introductory screen should be the TACO logo, the green leaves, and the title of today's presentation. So I see several hands waving. Excellent. So that means we're broadcasting okay. In terms of asking questions, if you could type in the question area, I will be monitoring the questions, and then I'll ask Brett to pause periodically so that we can answer your questions. And again, as a quick test, if someone out in the listening audience could type in a couple of sample questions so that we can see that it shows up okay. Yep, I see a couple coming in. Sounds great, looks good. Okay. So we got the questions working, and we've got the broadcast audio and visual working. So let me continue with my introduction, and then I'll turn it over to Brett so we can get started. Again, my name is Rich Medairos, one of the senior systems engineers at TACO. I am a mechanical engineer. I specialize in HVAC engineering and design, and I've been at it for several years. I am a PE. And talk a little bit about the company. The company, TACO, has been in business for 100 years. This year is our 100th year anniversary. And if it wasn't for COVID-19, we'd have several physical celebrations going on throughout the year, but we've postponed those physical celebrations until next year. So most of us are working remotely, except for the folks that are physically at the factory, and we want to give them a real shout out. They've been doing a terrific job under very challenging conditions to get all of our products out the door. So thank you so much for those folks back at the factory. The company is owned by John Hazen White Jr., and it is essentially owned by the White family. The senior leadership team is headed by Cheryl Merchant. Cheryl and her team are doing a fantastic job, especially in these challenging period of time. So that kind of gives you a snapshot of who I am, who the company is, and I'm going to turn it over to Brett so he can start his presentation. Brett, take it away.
Thanks, Rich. Appreciate that introduction. Hi, everybody. Good afternoon or good morning, depends on where you're located. Brett Zerba, applications engineer with TACO, been with the company almost 25 years. I do have a degree in mechanical engineering from the University of New Hampshire, and I continue to learn from Master Rich every day. He is quite the system HVAC engineer. Just take that for what it's worth, please. I do want to let everybody know there are some handouts available pertaining to today's installation, instruction sheets, installation recommendations sheets for if you ever get involved in one of these type of systems, as well as some more information on the one of the components involved with the system. So feel free to download those. And to let everybody know, this is a TACO Tuesday webinar, which you folks had to register for. So I know we've had some snafus in some of our other programs, but as far as I know, and as Rich knows, tomorrow, 24 hours after today's webinar is complete, you will receive an email with a link to the recording of today's webinar, as well as access to your 1 PDH hour credit for today's class. So hopefully that takes care of all the ground rules. Now let's get started. This presentation is kind of twofold. I'm going to present a PowerPoint and go over some items, both of these type of piping systems, and then I'm going to go over to the software that you can download from take a website. And we've had other presentations on the software, so hopefully many, if not all of you, are familiar with it, and show you how you can actually design these type of systems relatively easy with the software that you can download from our website for free, by the way, for free. HVAC solution, HSS software, the hydronic version. So the two piping systems that we're talking about, now this is hydronic distribution, okay? To get hot, cold, or maybe condenser water around a building to heat and or cool a building. That's what we're talking about. Now, hopefully many of you, if not all of you, have designed some type of hydronic systems. Last month, Rich focused on chilled beams, and he talked about chilled beams and the theory of them and why they're very gaining some popularity. So one of these piping systems lends itself more to chilled beams. That's the LoFlo system, and you'll see that very shortly. The LoadMatch system lends itself to a single pipe for a heating, heat pump, and believe it or not, chilled water applications as well. So let's get started. So here's an overview. Okay, here's an overview, and you can see, let me get my little highlighter here. Rich, I like this spotlight. Wish it was a different color, but that's fine. Anyways, where I'm
famous bouncing ball.
The bouncing ball. Boop, 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 boop. It's bouncing quite a bit today.
We could have a sing-along later, and you could use the bouncing ball to,
Oh, there you go.
Yeah.
Independent decoupled. I can't carry a tune worth a dang. Anyways, what I'm circling over here represents what I'm discussing. Okay, so this is a LoadMatch system overview, and it's a single pipe design for heat pump, heating, and cooling systems. There's a good possibility, if you chose to go in this direction, that you could save upwards of 40% of pipe and fittings can be eliminated because there's a lot less piping. And that lends itself to system savings, right? We want to talk about some of the positives, the benefits of a system like this. First cost, there's a potential for first cost savings, and maybe ease of installation. That's a biggie as well. Okay, so let's think about that as we go. And then we've done other presentations to many of you folks about primary, secondary, or decoupling, separation. There's different terminologies for it, and that's what all of these units are here, all of the terminal units. Now, this is a very simple system that we're looking at here. I don't think anybody can disagree. And by the way, don't take a picture of that. And it's not for what do you always say, Rich? It's not for consumption only.
Don't do this. Yeah, don't do this at home.
Don't do this at home. This is for presentation purposes. A good design engineer would add some other components to this design, I'm sure. So please do not do this at home. But nonetheless, I think you could tell some of the details of it anyways. So these units here are decoupled from the primary loop. They're decoupled from the primary loop. And that's the little twin T. And again, that green icon that my bouncing ball is on, that's our fitting called the twin T. That's the only proprietary part about a design like that, by the way. And there's other ways around a twin T, closely spaced T's. I didn't say that, but nonetheless. And you can get more information, and I'll show you a picture of a twin T later on in the presentation. And one of the handouts is kind of the catalog. Not kind of, it is the catalog. And all of the handouts that are available on today's webinar, you can also download from our website. This isn't information that's we're hiding or anything. It's available. And so instead of, I'm sure most of you are used to putting on some type of control valve, right? That the thermostat sends a signal to, that comes on, and water goes into the coil to heat or cool the room. Pretty straightforward, right? The thermostat wired to that, boom, it comes on. Well, instead of valves, we're proposing that you use circulators. All right, and there was a presentation not too long ago, Pump Fundamentals. We talked about circulators and pumps, right? And that they're the same. There's some differences, but they're the same, right? So it is a pump, but we like to call it circulators because it is a relatively small pump. And I know one of my good friends, Rick Mayo's on the line, and he can tell you a lot more about circulators than I could. But nonetheless, you're going to see some pictures of them very shortly as well. So no control valves. The zone temperature is controlled with circulators, and these circulators can be on off. In most applications, that's what we've seen, or variable speed. We do have some variable speed opportunities there, or options on some of our circulators. And if you think about, many of you in the audience probably still considers TACO the double O company, right? Our main product for many years, or what we were known for, was the double O circulator line, right? The 007 is a name terminology, a product name that is very common in the marketplace. Well, these circulators are very similar to those. There's a couple of differences, and I'll talk about those very shortly as well. And you can kind of see down here a little detail. Let me get to a drawing. Where can I draw? Oh man, I don't know how to draw here. You might want to add some type of vent here as well to get some air out. But nonetheless, that's pretty much what the terminal unit would look like, right? The circulator, and some are mounted inside the terminal unit, the case container or box or whatever, or others can be mounted by the contractor at the job site as well. And then another benefit or potential benefit is very little balancing in a system like this. They're self-balancing. These zones are guaranteed to get the flow once things are operational, right? Once things are operational, to get the flow that is required because the circulator's size to get that flow. And you'll see what I mean by that when I move on. But this is a overview of a single pipe system. And let's look at another picture to kind of get into some more of the details. Oh, first off, I got to erase this picture. My friend Rich forgot to tell me how to do that. How do I do that? Drawing tools, erase all drawings. Ah, I did it. All right. Again, one of the biggest advantages, besides maybe the ease of installation, first cost, lower horsepower, is the self-balancing. If you've been involved with some projects where there could be some balancing, or you've had some balancing issues on a system like this, once the main piping line, once this has the right flow going through it, right? So this is a single pipe, so it's all based on the primary pump. But many piping systems have many loops, so you'd have a balance valve on the main loop, and once that 100 GPM for that loop is set, as long as the pump's operational, then these zones are self-balancing. The zones are self-balancing, and that could be a big savings. You don't have to go out there and things change in the system, and somebody closes some valves or plays with something, but you're still going to get the proper flow to the terminal units. And the other one that's a little harder to talk about is the system is very forgiving. It's very forgiving because all of the BTUs in this loop are available at all times to these loads as it goes around. And I'm going to talk about the proper sizing of it and calculations and whatnot, because I'm sure some people might be already typing in questions about well, what's doesn't the temperature warm up? What about the Cascade? So anyways, we will discuss that. But if these guys shut off here, that cold water is now available for here, or colder water. So it's very forgiving. And because it's in series, all BTUs are available at all terminal units at all times. So something that's pretty helpful and very important in a heat pump design. Many folks that I've seen or worked with on this type of design, single pipe design, use it on a heat pump application, maybe before they dive into hot water or chilled water. Chilled water, we get a little nervous about dehumidification, although there's studies and whatnot that shows you can do that, and maybe anyways, I digress a little bit. But if you have a heat pump system, you're going to stay within that 70 to 60 or 60 to 90 degree temperature range, and that Cascade doesn't really affect the output of the heat pump, right? You put in a 2-ton heat pump, And if you have 60-degree water or 80-degree water going in there, you're still going to get the BTUs that you're expecting in the room that you've designed for, right? So just kind of think that through a little bit and whatnot.
Hey, Brett,
Yep.
we did get a question on your previous
Awesome.
slide.
Awesome.
Yeah, the question
This
is
one or this one?
The next one.
Okay.
I think it applies to both, but
Yeah.
so the question is the primary pump constant volume or is it equipped with a variable frequency drive and variable volume?
Great question. I apologize for not mentioning that. You can do it either way. In most systems, it's variable volume, and instead of pressure changing it, changing the flow, pump speed, it's delta T that changes the pump speed. So you would measure the temperature going out. If you want 12 degrees on that chiller, once that temperature starts fluctuating down because loads are cooling, shutting off, you would slow that pump down. Opposite in the heating application. So you've got maybe a 20-degree, 30-degree delta T from 120 to 150, right? As that return water starts coming back at 125, 130, you would send some signals to the pump to slow down. So all the stuff would be done in the mechanical room. You wouldn't need the sensors out in the system. Hopefully that answers the question.
We have a follow-up question, Brett.
Yep.
The follow-up question is, how do you maintain the minimum gallons per minute? Do you need a bypass on that main loop?
Yes, yes, yes. Again, please just realize that this isn't for consumption at home. So yes, there's some finer point details required to maintain a minimum flow rate. Correct. Thank you for pointing that out. Hopefully that gets us where we're going. You have anything to add into any of that, Rich?
Nope, but there's a question for another individual. It says, won't the farthest zones from the chiller source suffer under the full load? And I think he's talking about the Cascade, which you're going to get into in a few minutes.
Yeah, I'll get into that. And the answer is, as long as you consider the design and there's the proper delta T and you have enough flow in here, and this one's designed accordingly, that temperature entering that one there would still be suffice. So I'll talk about that a little more when we get into the cascading. So give me a minute or two on that one, please. And one of the key items, another main, we like to get this across to folks like yourself, because sometimes people get a little nervous about adding pumps to a system. The circulators are very, very reliable, and green ones for sure. Other colors are reliable as well. And I say that because we're adding pumps to a system, and sometimes people get a little uneasy about that. But these are circulators. There's no seals. It's a wet rotor circulator, no couplers, no bearing assembly. It doesn't require lubrication. And this is the guts. Oh, let me get my bouncing ball again. So I apologize for that. This is what sits in this canister here. This is a variable speed one. If that board wasn't there, that bracket and board wasn't there, that would be our more traditional on-off one. But this canister is what sits in there. Wet rotor sits in here. That's the impeller, and that sits in the wet end. And then there's a shaft, right? And that's all enclosed. And the system fluid, the nice clean system fluid, lubricates the bearings that are in there. So there are no assemblies that need to be lubricated. Very, very quiet. Most applications, when it's on, unless you touch it, you don't even know it's running. It's pretty straightforward in that regard. No strainers or valves to clog. It does allow some impediment, but we do recommend that you put you really do clean that water. You want pretty clean water going in there. And our circulator has a nice warranty controlled compared to control valves, and I'm sure probably others would offer the same thing in that regard. And then for chilled water applications, we actually offer an integral condensate baffle It's kind of differentiator for us. It's just a little spacing plate here that gets the motor housing away from the wet end for chilled water application, so there's no premature condensation causing failure. So we think, and others that have utilized them feel that it's a better maintenance thing compared to a control valve that could maybe cause some other issues. And there's a leak path on those, and there really isn't on here. Twin T, the Taco Twin T. Again, this is the proprietary part, and there's a handout with more information, or you can go to our website. Simplifies piping, reduces labor, eliminates some joints, and it guarantees that the terminal unit is decoupled. That secondary circuit is decoupled because the supply and return is at the same point along the main flow. So when you look at it here, right, I mean, obviously the relationship might be a little easier to see down here, but now that there's no spacing here, you won't get, whoop, what the heck happened? Anyways, there's no spacing down here, and so nothing will, you won't get any flow in the wrong direction at different times. So that's why we offer the Twin T. There's other ways to do it. Many of you know how to decouple things in primary, secondary, but nonetheless, this is a fitting that is available for many of the applications. So let's talk about the Cascade. It's really, and when I do my designs on the software, you'll see it even better. Cascade is controlled by the ratio of the mixed flows. All right, you can kind of see what's going on here. There's mixed flows, right? A fraction of the GPMs go down into here, and it warms up. And excuse me, this is hot water, so it cools down. And then when that mixes back here, the next guy, worst case, sees a little cooler temperature. The way to control that is to make sure you design your delta T across that main. So I've seen people, so think of a hotel design, right? So you have a 4-story hotel, and there's runouts on each floor to pick up the coils. I don't care if they're hot or cold or whatever. So you want to make sure each floor is getting the correct GPM across that main, and then the Cascade stays within the range that you've designed it for. Hopefully I'm explaining that understandably, but when we get to the drawing and when I draw up 1 or 2 systems, you might see it a little better. So Cascade can be minimized by increasing the flow in the main loop. So really it's dependent upon how much flow you put across here. I've seen people control that flow with valving. They made it a little more complicated than maybe they needed to be, but they were a little concerned about that. But nonetheless, and another thing I'll show you when I do a design, see this pipe here? The main pipe is 1.5 inches. In most single pipe designs, the main piping run out is the same diameter as the first pieces of pipe in a 2-pipe system. If you think about it from a practical standpoint, that set of zones that are attached to the loop are getting the same BTUs, right? That's coming from the mechanical room, the boiler, the chiller, whatever. So that first set of pipes are the same diameter, right? And a 2-pipe system, and this type of setup, it would be 1.5 inches, and then it would go down as the flow rates peel off. In the single pipe system, it's the same diameter all the way across that runout. So that back to that hotel design I was talking about, it would be 1.5 inches across the whole floor from room 1 all the way to room 20 or 30 or 40. So just kind of keep that in mind. In the worst case, the last terminal unit sees around what's going to go back to the central plant water temperature design. And then conservatively, temps are calculated if all units are on some of the peaks. So that's kind of what the Cascade, it's not kind of, it is what the Cascade is what we talk about. So if you think about a heat pump design, right? This one could be heating, this one could be cooling. So that temperature is going to kind of moderate and stay the same almost, right? So you can heat and cool build rooms, zones with that heat pump design very, very easily with a single piping loop. So hopefully that gives you some idea what I'm talking about with the Cascade. But like I said, I will talk about it some more and point it out some more when I do a design or two. So Rich, I'm going to the low flow piping. This is for chilled beams now. This is a little more specific application or system. I don't know if there's any more questions you want to bring up, or do you want me just to keep going?
Yeah, I wanted to keep going. There's no new questions.
Okay, good.
So yeah,
Good.
let me move along.
All right, so next up, the batters that's coming up next. Actually, there is baseball we can watch, although I am a Boston Red Sox fan, and I haven't watched many of their games because it hasn't been much fun. I think they've lost 7 or 8 in a row now. It's historic what they're going through. But nonetheless, I get back to low flow piping systems for chilled beams. So if you've worked on a chilled beam project, you might be used to what I'm showing you here. This is the conventional a type of distribution, right? You have some regular temperature chilled water. When I say regular, I'm saying going out at 42, 45 degrees to satisfy the DOA, dedicated out there units. And I wouldn't be surprised if you have that water going out to some other zones as well. I know at our facility in Cranston, Rhode Island, that Rich worked very hard on when he was in a different career. We have some entrances into the chilled beam area or into the area that's chilled, cooled by the chilled beams, and we have fan coils there to take care of that inrush of air. So you need cold water there too, right? When I say cold water, I'm saying below, your normal type of cold water. So this is what you would normally see, and then you also need high temperature cold water, or whatever you want to call it, right? Usually above 55, 58 degrees, above the dew point, because Rich went over all of the possibilities with humidity and dripping and whatnot. So any water, any cold water that goes to a beam has to be above the dew point. And so normally I show a range of 58 to 62. So somehow you have to have potentially two piping systems, distribution systems. People do it with heat exchangers. People do it different types of ways. And then here's kind of how complicated that can be, right? Potentially, right? There's, in this case, I see at least 4 pipes coming out of the mechanical room. And again, maybe there's a heat exchanger instead of a second chiller or something. But nonetheless, you do need cold water, cold, regular chilled water, and high temperature chilled water to satisfy what we're talking about to cool the rooms. Okay, here's an alternative. Here's an alternative. We call it low flow radiant chill beam injection pumping. So again, kind of similar, right? You see the single pipe going around, right? High delta T at the chiller, right? So we can pick up the zones that require the cold water first. It depends on the piping layout or however you want to do that. And instead of mixing in the mechanical room to get the lower temperature water for the chill beams above the dew point, we propose to mix at the zone, okay? And I'm showing one chill beam here. There's a zone at our facility that has 9 chilled beams attached to it. Our big classroom. Hopefully, some of you have been to our classroom. I seen some names earlier before we started, so I know some of you have been in that classroom. So I only represent one here. You can connect. You have one of these low flow blocks, we call them, for each zone, not for each chill beam. But nonetheless, we're proposing to mix at the zone. And there's other folks that have that thought process out there as well. I believe Semco is somewhat similar to this. There's always differences, but nonetheless, they propose something to this effect as well. So keep that in mind. That's what we're thinking. And here's a injection piping more detail. So you got the 2 circulators, and I'm going to show you a picture of the low flow block very, very shortly here. Excuse me. I forgot my bottle of water. I'll keep going. I'll dry it out. And you'll see this one injects cold water here, and this circulator satisfies the zone. So when it doesn't need cold water, chilled water, it just runs through the chilled beams. And then as the water temperature returns, comes back closer to that 62, this one's going to start injecting off of this main loop. So you can see, again, you got the cascade of temperatures, but it's not as critical because you're not dehumidifying per se with this, right? We're dumping the dehumidified air, although active chill beams pull off a little bit of it, and that's the whole detail about chill beams. But we are dumping the air into the room without the moisture in it, right? We're separating that out. So that's why you can satisfy the zone temperature even with these temperatures getting up a little higher. And we do this at our facility. It's a two floor building. Our classrooms are downstairs, and we have offices upstairs and some conference rooms and whatnot. And we have a single loop for chilled water and a single loop for hot water doing this type of injection. So it's something to consider. It's a different approach, just keep that in mind. And here's a picture of the low flow block right here. I mean, obviously it takes a little bit to support it, and ours are located. Actually, you can see them through some panels because it's a kind of a showpiece at our facility. And this is the zone circulator's constant speed running out to the zone, and this guy's variable speed, and it ramps up and ramps down to inject water into this header, cold water, right, to get that temperature to the right application. To the right temperature to satisfy the zone. There's controls associated with it. I'm not going to get into all the controls today because I want to cover some other things, but nonetheless, that's the low flow block as well. So, Rich, I have completed the PowerPoint part of my presentation. If you would like to add something, feel free. Or are there any questions that?
Yeah, actually, a couple of questions did come up, and one is there a control to keep chilled water above the dew point for the beam installation? Is there a control strategy?
Yes, there is. And Rich, would you mind explaining that a little better? You're pretty good at it.
Yeah, you'll have to point for me.
Yeah.
So let's take that first active chill beam. Yep, that one right there. And the supply water temperature is entering the low flow injection pumping unit, low flow mixing block at 50 degrees Fahrenheit. And we're actually going to use a controller. We have a controller that we call the CHB, which stands for the chill beam controller. And what it does is it monitors the discharge temperature. See that 58 degrees? It monitors that temperature, and it controls the injection pump. So the injection pump is the first one, and the zone pump is the second one. The zone pump is typically on-off constant flow, and the injection pump is typically variable flow. So we vary the flow of the injection pump to maintain a set point temperature, in this case 58 degrees, which is generally somewhere between 3 and 5 degrees above the dew point temperature. And as Brett pointed out, the unit on the left, the fan coil, that's representative of the DOAS, or dedicated outside air system, that typically wants the coldest water off the loop so that we can dehumidify the air. Because remember, the chill beam has not only a hydronic connection, but it also has a ductwork connection, and it gets its primary air from the DOAS unit. And that primary air has to be dehumidified so that when it enters the chill beam, it provides the latent capacity required by the space. So the injection water temperature at 58 degrees, just repeating for a moment, is above the dew point temperature. The chill beam is not controlling the dew point temperature hydronically. The chill beam is controlling the dew point temperature via the outside air temperature that's coming, not outside air temperature rather, but the supply air temperature that's coming from the dedicated outside air system in order to provide dehumidification. So there is another question, advantages of high delta T in the chilled water loop, advantages of pumping versus two-way valves. That's a great question. So as Brett pointed out earlier, in the terminal device, there is no control valve, and because the pumps are self-balancing, there's no balancing valve. So the added resistance of the control valve and the balancing valve is not in the terminal device. So the unit farthest to the left, that's a single circulator. The fan coil unit, which represents the dedicated outside air system, that's a LoadMatch circulator. And then the one that's serving the chill beam is a LoFlo mixing block or injection pumping. So the main loop, as Brett pointed out, could be as high as, say, 16 degrees, 42 to 58, but the actual delta T across each individual component could be customized. So for the chill beam, the difference in temperature is 4 degrees, and the difference in temperature for the dedicated outside air unit happens to be 10 degrees in this case.
And
Hopefully we've answered those questions.
the bigger the delta T, the smaller the pipe because of the flow rate going around there, if
Right,
that kind of makes sense.
And the smaller the pump.
Right. The smaller the pump and whatnot. So there's some savings. One of the savings that when we get into a bigger discussion about this for a couple hours is the possible electrical savings with not needing as much horsepower in the system as well. And the ductwork is a lot smaller as well, but that's chilled beams. That's not necessarily the LoFlo. That's just some other details there. Great questions though, huh, Rich?
Yeah,
as usual, the staff is coming through for us.
Excellent.
Excellent. So
okay, no further questions at this moment. So why don't we continue?
All right. So I brought up the HVAC solution software. All right. And again, you can download that from our website. Forgive me because I didn't have my website, the TACO website open. But if you go to the TACO website, this is the main page. By the way, there's Brett and there's Rich, two very handsome guys. But if you go to the main page and click on apps, TACO Design Suite of Software, and there's the click there, and it has to go on your computer. But we've done other classes that get into the details of that, so I want to get back to it. I did want to at least show you that it's available on our website. Here's an example of a project, a LoadMatch project that we did, and I'm going to draw up some. So this is a dorm project for Cedarville University in Ohio that was proposed and actually installed, but very, very simple. Right, here's the cooling tower, and again, this is a rough, not a rough layout, but it gives enough information for the design engineer to finalize his MEP drawings and whatnot, the sizes and stuff. But I'm sure there's more details associated with a lot of the maybe around the boilers or around the tower or whatnot. The heat exchangers, some shutoff valves and stuff like that. So please don't use this one verbatim. But here's the key component of it, right? Like I said, so this is coming out of the mechanical room, right? There's a balancing valve here to guarantee. This is only one loop. This is a 2-story building. Many applications, there's one loop on each floor, and they're not necessarily connected together. But you can see that one loop goes here, scoots up at the end of the hallway, comes back down. Think about it, the contractor, how relatively easy it would be for him to lay out that piping, right? He only has to get to the job site, especially for the mains. He can figure out the spacing between each one and put the twin T's next to and do a lot of the piping at his factory and bring that to, at his shop and bring it to the job site and hang that piping main relatively quickly, very, very quickly. So there's something to consider. And you can see that this software shows you the cascade temperatures here. It shows you worst case for heating and worst case for chilled water. So you can, or cooling, I should say. It's not chilled water, right? It's condenser water because these are heat pumps. And you can kind of see how easy that is. And this one here had a heat exchanger in between the tower and whatnot. And it's not unusual in certain climates to have backup boilers. I've seen some of the heat pumps have electrical backup for the heating. But you know, once you get above a certain longitudinal line in the United States, I think it's a better design maybe to have a backup boiler. But I don't need to get into all of that necessarily detail in this discussion. I did want to at least show you an example of a heat pump design that is load match, right? Single pipe. And again, each one of these loops had some shutoff valves and an air vent and whatnot. And if you read one of the handouts about starting it up, here's the way to start this up, right? You got to turn on these main pumps as long as the water system's filled, right? Have all these units shut off, and you run that loop over with the weekend, right? And let the air and dirt separator clean the system out. Boom, and now you just go in and start up each of the circulators, each of the zones the next day or that Monday, right? You Friday afternoon, you get the system running and clean it out, right? Boom, and then on Monday you start making sure you can get water to each of the circulators. And that's explained in the installation instructions as well. Let me go to my other picture here. This is an actual project. Actually, I think one of the individuals that was involved in this one quite a bit. This is a hospital medical facility, and this is one floor. This is a chilled beam layout. So what they chose to do in this project, because of the savings in pipe and the ease of the controls, relatively ease, our control systems and whatnot, on each floor, for the chilled beams, they're using the LoFlo block. So this only represents one floor. So this chiller is kind of just representing getting cold water there. If you know this software at all, and you can kind of see it's just a big loop, right? And one of them picks up a bunch of active chill beams. You know, I don't remember all the specifics, but you can kind of see how easy this is to run around there. And again, there's that cascade we talked about, right? You can see this tells you the injection. This tells you the zone, and there's those temperatures here. And you can adjust these. This one here, we showed a 5-degree delta T. So working with the engineer, and really the controller can actually adjust that as well, our CHB one and whatnot. So just keep that in mind. I did like to at least show you a couple of examples, right? I advertised I was going to show some examples, and now I'm going to draw some up. Any questions,
Brett,
Rich? Yep.
Yeah, before you go to the actual design, question came up. Can you explain how the mixing block works? If you could zoom in on the mixing block and just zoom way in and tell them how that thing works.
Okay, so this is the low-flow mixing block. You can see there's a bunch of them here, right? So as Rich was mentioning, this is the injection side of it, the circulator that's attached to it. And this is another circulator, that's the zone circulator, okay? So Rich, correct me when I astray, but the thermostat that's located in where this ACB is located, right? Maybe 4th floor or whatever, wherever it is, tells that we need cold water. We need chilled water, right? We need cooling in the room. It turns this circulator on, right? And then there's a temperature unit right here monitoring that temperature. So as this water runs through here, it runs like this because nothing's coming off of here. So it just goes through this block and keeps going. It's like a decoupler, right? As this temperature starts to scoot up 58, 59 degrees, the CHB controller says to this circulator, start coming on slowly and start giving me some of that 57 or cooler water to inject into here so this unit can start to cool down. It looks like some of these numbers could be off here. I may have a setting wrong. I may have copied the wrong one, but nonetheless, as this cooler water from this loop goes into here, that water comes back down to 57, and it can satisfy the load required in that zone, the sensible load. So hopefully that explains it. I don't know if I did a good job of it or not, but nonetheless, you can kind of see that even better on this one here. So
yeah, so the only other thing I would mention, the chill beam controller actually is looking for input from a wall-mounted temperature humidity sensor.
as
So
well.
it monitors the space temperature and relative humidity. It calculates based on that data the dew point temperature. So let's say in this case the dew point temperature is say 50 degrees Fahrenheit. Then it will set the injection pump speed in order to maintain some predetermined temperature above the dew point temperature. So if the dew point temperature, say, happens to be, say, 52 degrees, and then they want to maintain 5 degrees above, it's going to maintain 57 degrees in the pipe itself. And so that's fundamentally how the low flow mixing block works. Hopefully that answers the question. Actually, it says, somebody said, maybe explain the low flow mixing block as a small hydraulic separator. Yeah, I think Brett had mentioned that. It's actually, there's a hydraulic separator in the low flow mixing block, and there's a hydraulic separator in the twin T. So that main pipe, the 2.5 inch running from left to right, is actually the primary circuit. The circuit for the injection pump is the secondary. So you have a primary, secondary, and then the zone pump winds up being the tertiary. So you have two loops, the primary secondary loop and the secondary tertiary loop.
And if you remember, what we're proposing with this type of system is to mix the water temperature at the zone instead of at the mechanical room. So that's the thought process here. And if you use the control, the TACO controller, CHB, and the rest of our system, there's a potential for a big price savings on that. So anyways, let me show you how I can use the software to design both types of systems. I'm going to use the wizard to do this, okay? So if I click on the wizard, so I'm on the HVAC software. We've talked about this before. Hopefully this isn't all that new to most of you. I'm sure there's a couple that haven't seen it, but nonetheless, you can see some tabs here. It's a Windows-based program. I'm going to click on Wizard, Hydronic, and I'm going to click on System. Okay, so I'm not going to open an existing one. I'm going to create one. This one's going to be a LoadMatch system. All right, so that's the first type of system. And I'm going to do it for a heating combined schematic. So I'm going to do a heat pump design. Okay, heat pump design. I'm not doing changeover, right? Please keep changeover out of your discussion for today. We're doing a combined schematic, so the heating and cooling is in one loop per floor. So I'm just answering some questions here. Number of loops. So let's do a 4-story building. All right, so I'm going to do some horizontal distribution, 4 stories. Horizontal, right? Horizontal loops. So there'll be a main pipe running down. Just think about a simple hotel. I know many of us haven't been to a hotel in a long time because of COVID, but nonetheless, there are some out there still. Think about a simple 4-story hotel, and there's in the hallway, there's going to be a loop running down each one main loop, okay? And I'm just going to show the mechanical room up on the roof for now. All right, hit next. Number of loads. Instead of making a real big one, because we're kind of getting pressed for time here, I'm just going to put 6 zones on each load, on each floor, okay? And I'm going to show them below the piping. You'll see what I mean by that. It's just kind of the way that it shows it. And I'm going to use this data for the remainder of the loops. None of these questions have been too complicated yet once you go through it. Hit next. So I'm going to use a heat pump. I'm not going to put in a manufacturer. I'll just use no manufacturer, and I'm going to hit next. This is where I can put in the designation. I'm just going to put in the same thing here, and maybe a 2.5 ton heat pump. Got to make sure I, not, is that 30,000? Yes, it is. And then you can see here, it actually has, it takes into account the COP and EER. All these numbers are adjustable as you work through it, but we don't need to get into all of that detail. but please, you can adjust any of the numbers that are shown on this screen. So I'm going to use a boiler, and I'm going to use a cooling tower. Pretty straightforward, right? I could actually use a ground source if you wanted to do ground source type of design. Hit next. I'm just going to put in one boiler, and I'm going to put in one cooling tower. And I could put in glycol, but I'm not going to for this particular application, but I could show glycol if I needed to. The heating, I'm going to use primary, secondary. And since someone mentioned hydraulic separator, I'm going to put in the hydraulic separator. That's a Takeo 5900 product that we've actually done some presentations on as well. And then I'm going to do cooling is just manifold primary. And the definitions of each piping system is over here on the right. And if you ever played with the software, go through it a couple times and you'll see what the differences are. Hit next. The primary pump, this is the pump attached to the generation equipment, in this case, the boiler, right? So I'm just going to show a little vertical inline. The secondary pump or the building or loop pumps, I'm just going to show another vertical, just to kind of get through this, 2 KS pumps. Hit next. Number of pumps. Now, see, this is asking for cooling, but the cooling and the heating are the same, so I don't need to answer the question again. Hit next. Expansion tank. Air separator, I'm going to put in that 4900. This is the coalescing inline type of air and dirt separation. We recommend it for all hydronic designs because it really eliminates air and dirt down to incredible numbers to help protect all the pieces of equipment, especially the pump seals and others in there. Hit next. I'm not going to save this file. I hit finish, and boom, there's my heat pump design. Right, I can hit Control A for some of you that remember. Connector annotations diameter, and there's my the beginning of my heat pump design very, very quickly. Now, watch what you can do with this if you need to do some comparison shopping. If I go back to system, it remembers all of my answers, and watch, I can go, I'm going to change this to a direct return and hit next. It remembers all of my answers, so I'm just going to scroll through quickly. Next, 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 next. Just don't go too fast at the end. When you hit finish, don't go dub, dub, dub. You'll mess up. If I hit finish, it brings up the 2-pipe design very quickly as well. And if I hit Control A, please come out to the same diameter. And, oh good, I wasn't fibbing. Notice the two-pipe design has a 2.5-inch supply going in, right? The control valves, balance valves, whatever. And then over here, my single pipe is 2.5 all the way across. But now you can very quickly show this or potentially show this in a presentation or to the contractor. And what do you think? Can we save some money by doing it this way or something to that effect? But nonetheless, this is how easy you can get a starting design with the software to do a LoadMatch design, single pipe design. So now let's do one for a chilled beam. All right, so I'm going to get a new sheet of paper. That's not hard, I hope. Go back to Wizard, System, hit Next. In this case, I'm going to do a Takeo single pipe. I'm just going to do cooling only. Okay, I'm just going to do cooling only, but you could do both. Number of loops, I'll leave it at 4. And again, I'll leave the mechanical room up top and the flow direction to the right. I'll put 6 zones on each one and the load orientation below. I hope when I get to the end, I'll actually show you what that means, but I think most of you could pick that up. Hit next. This case, I'm going to choose an active chilled beam. So notice options, use LoFlo mixing block instead of circulator pump on load equipment. So that checks. So you'll see what that does for us very, very shortly. There are a couple beam manufacturers in here. I'm not gonna use any of those for this type. And you can see there's all different types. It's really just a picture. I'm more concerned with the hydronic distribution design when I do my or suggestions with using this software. So that's just me, okay? So obviously I'm the hydronic guy, right? So I'm worried about the pumps and the piping and all that. So the other people need to worry about more about the active chill beam when you blend everything together. But this does show that picture. Hit next. So I'm going to change this to ACB, and I'll just leave it at the call outs here. Hit next. So this time I'm just going to choose an air-cooled chiller just to kind of get through this pretty quick. Hit next. I'll just show one chiller again, just for simplicity, manifold primary again. Hit next. Right, couple of pumps on there, suction diffuser, vertical inline. Hit next. Expansion tank, air separator. Again, we recommend it on all of them. We sell the other ones, but nonetheless we recommend it. And hit finish. And there's my chilled beam design done very, very quickly for you as well. And again, if I hit Control A, right click, connector annotations, there's the diameter of pipes. So there's a quick way to do a chilled beam design with the software as well. And then you can go in and start adding in other loads and whatnot. And you can see the cascade, the injection going on here and taken care of. And notice this one's 42. So I want to set this temperature, the return temperature in the chill. I should have done that when I went through it. Maybe I'll set it at 56 for this case as it recalculates. So this one here is injecting in at 42. If all of these zones are calling, the last one's going to inject in at 53. Okay, so you can see it's a little higher flow rate going in there to satisfy that. You can see that that variable speed circulator may be getting in different flow rates into each of the zones. And then you could start playing with the correct numbers over here and the delta T's and whatnot. But I did want to at least show you how easy, potentially easy it is to do a layout utilizing the software if you choose to use the wizard. So, Rich, I'm getting parched.
I think you're doing a terrific job, and we're actually getting close to the end here. We only have a couple of minutes left, so this is a good point in which we can pause and see if we take any more questions. Anybody have any questions out there now that they've seen the different applications for single pipe, both in terms of load match with a circulator and the low flow mixing block? Anybody have any questions out there?
Awesome.
I'm not getting anything typed in. I'll hang in there for a few more seconds while we chat here. You don't have to ask technical questions. You can ask other kinds of questions. For example, you can ask, how old is Rick Mayo? Let's see if we can get Rick to admit to his age. Or you can ask, generally I had yesterday, I don't know if it was yesterday or the day before, I had a contest. Whoever could figure out the weight of my 11-year-old golden retriever. The closest guess without going over, they get a free gift certificate to $5 footlong by the appropriate rep in their area of the country. So if you get the right answer, then you'll get to be taken out for lunch and treated to a $5 footlong at Subway. Okay, a question did come up. Is the software downloadable from your website? And the answer is yes. Brett, show that one more time, Brett.
Can you see it, Rich?
Yes, I can.
Okay. I'm on the website. I'll go back to the home page just to go through the procedure again. The quickest way, there's probably other ways to get there. Apps, Takeo Design Suite of software, and you click on the software and download HS2 software. So the answer to that question is yes, and that's the procedure. And the Takeo website is www.takeocomfort.com.
So I did have a guess, Brett, as to my oldest golden retriever. They said 76 pounds. Nope, she weighs less than 76 pounds. See if we can get anybody can correct the guess weight without the closest weight without going over. So it's definitely, she's less than 76 pounds. Any other questions out there? It says, up to, let's see, how many cold beams can be installed by a low-flow mixing block? I think the low-flow mixing block limitation, what's the GPM limitation on those circulators, Brett?
Yeah, I think we go up to around 25 GPM.
Yeah, so if you zoom in, say for a moment, typical chill beam is somewhere in the range of, well, a
This
zone.
one here shows five. This one has 5 chill beams, so I need
Yeah,
12 GPM total. So it's
yeah, so
what, two and a
that's a
half
little
each
over
one?
two GPM per chill beam. So
Right.
yeah, there are some
I,
limitations.
I have seen for bigger zones, to kind of further answer this question, I have seen for bigger zones where possibly because just there's so many, the zone's so big that half go on one control on one low flow mixing block and the other half go on another one, and then the controllers kind of got to communicate together. So I have seen that. Uh,
We're
just keep
getting
that in
lots of guesses on the weight of my dog, Brett.
mind. Awesome.
Yeah, we've got as low as 52 pounds and as high as I said 76 pounds. So why don't we just before we sign off, I'll give you the actual weight. But at this point, Brett, do you have any last words you want to say before we go? It's 1:01 right now.
Thank you, everybody. I appreciate your time. I know how valuable time is. Hopefully you got a little bit out of it. There's a lot more information on our website about both of these systems, and you can contact Rich and/or I or others to get even more information. We will help you with designs as well. So, Rich, take it away. Thank you again, everybody.
So thanks again for participating in today's presentation. A question just popped up, very last minute question. It says, which field controller is being used to control the pumps of the mixing low flow? So we have a controller called the CHB, which stands for the chill beam controller. And the most common one we use is called a CHB2. And that's probably, it's such a popular controller that we actually have provided our controller with a chill beam system in buildings where they might be using, for example, a Medairos for the main system. They'll use our controller for the chill beam system itself. Okay, the very last thing I will tell you that my 11-year-old golden retriever, her name is Daisy, and she weighs 70.2 pounds. 70.2 pounds, and her weight has been constant over the last roughly 10 years after she became full grown. So, yep, 70.2 pounds. Someone was close.
Awesome.
So with
All right.
that, I'm going to say thank you once again for participating in today's webinar. Stay safe out there and take care, everyone. Bye-bye for now.
Bye. Bye.